So this brings us to the second tutorial talk today. The talk is from Professor Ernst Bauer from Vienna University of Technology. So I would like to first introduce Professor Bauer, and he actually obtained his PhD in 1984 from Vienna University of Technology. And then he get his postdoc lecture qualification in 1991, and then become a professor in Vienna University of Technology since 1997. In 2009, he was awarded a university professor at the university. His research actually is focused on strongly correlated systems in extreme conditions, including superconductivities and thermoelectric materials. Actually, Professor Bauer was very famous for discovering the non-central symmetric heavy fermion superconductors. So, and he actually was the head of the European Union cost programs, and also the chairman of SCAS on 2005, and also was the head of the Chemical Society, Chemical Physical Society. In 2013, he was received a Christian Doppler Laboratory for Thermoelectrics, and in 2023, he was awarded the Outstanding Achievement Award of the International Thermoelectric Society. He has published more than 550 papers in international journals. So now let's welcome Professor and
So thank you very much for this very kind introduction. Ladies and gentlemen, thank you for coming back after the lunch break. I have a very difficult task to continue after this very good lecture of Pierre's in the morning. But I will switch a little bit gears, coming from very basic physics to basic physics, where we do see also some application. And the field I'm working in right now is the field of thermoelectricity. So in the next 2 hours or so, I will guide you through basic principles and then show which materials are right now in the near to be applied in daily applications. Okay, after some technical problems, I hope I can continue without problems. So here is a list of people having contributed to this research in the last 10 years or so. And for about 7 years, I run an Austrian research project, which is called Christian Doppler Laboratory. So you all know Doppler. Christian Doppler, he was an Austrian physicist, and he found this very famous Doppler shift, where many scientific branches today are dependent on. And such Christian Doppler laboratories are established in different fields of techniques. And the goal is to help industry to develop their research on a quite good level. And for this, industry has to pay 50% of all money in real money, not only in kind. So there is another program which supports my research in Vienna, and this is founded in Japan by JST. The motivation which we have since a long time is to search for cheap and stable thermoelectric materials, because right now the most popular thermoelectric material is bismuth-2 tellurium-3. So tellurium is a very, very rare element, is a little bit toxic. And so the application in big styles is not quite easy, and especially in Europe, where we have a lot of laws which are going to forbid elements like lead or other slightly toxic elements as well. And since I'm working since a long time in the Institute of Solid State Physics, in this field, we like to understand our measurements which we are doing. We not only like to say, if we make a measurement, look, the curvature goes up, and a little bit later it goes down. We like to apply physical models on a good level and extract from fitting experimental data a number of reliable physical quantities from such a fit. Now, let's start with thermoelectricity. Possibly not all of you are quite familiar in this field, because differently to strongly correlated electron systems and to superconductivity, which plays mostly in the range of 4 Kelvin or below, even in the millikelvin range. In thermoelectricity, we have just the opposite. We go up above room temperature, so the world does not end at room temperature. There's a lot of interesting physics and features above room temperature as well. And thermoelectricity is one of such branches which is living from high temperatures, as I will show in a minute. To introduce you into the field of thermoelectricity, you can do it tonight as well at home or in the workshop of your parents. By sure, you will find different wires, for example, a piece of copper wire and a piece of iron wire, and just wrapping such wires together, as it is shown here in this graph, and heat up a little bit one end of these wires, for example here, then go back here, then you can measure on the opposite ends of this wire already a voltage. So this voltage is created just due to the fact that we do have two different temperatures here, a larger temperature and a smaller temperature. And then if you put some ohmic resistor on the previously open ends of this wire, an electrical current starts to flow, and this current is driven by this voltage which has been established by these temperature differences on both sides. So we can create from a temperature difference, from thermal energy, electrical energy, electricity, current and the voltage. Current times voltage makes electric power. So without any machine or with any generator, just by converting heat into electricity. And this phenomena, you know all, is called the Seebeck effect, which is a quite old effect. I will show a picture quite soon. As long as we do have different materials, and as long as we have different temperatures, there is always a voltage created. Depending on the type of materials, this voltage can be large or it can be small. Clearly, many people around the world, there's a large community working in the field of thermoelectricity. They are searching for materials which do this conversion from heat into electricity on a higher level than it was done previously. Unfortunately, all the good metals and other materials we know are very bad thermoelectric materials. And as I will show, usually we have to look for materials which are near to a metal to insulator transition. So bad metals are a good starting point. And after this, one has to look for systems which have a gap in the electronic density of states near to the Fermi energy. Now, altogether, we do know 3 different thermoelectric quantities. I have already mentioned the Seebeck coefficient, and here is a sketch of a thermoelectric generator. At the moment, we need not to know that usually we do have 2 different types of materials, a so-called B-type and a so-called N-type material. In the former, holes are the charge carriers, the majority charge carriers, and in the N-type material, the usual electrons are the primary charge carrier. So if we have a piece of material and have on the one side a large temperature and on the other side a small temperature, the hotter electrons will diffuse to the cold side. And because then there is an inequality of electrons between the upper and the lower side, an electrical field will be created. And this electrical field will prohibit that further electrons will flow from the hot to the cold side. So, and it is just this electrical field which is responsible for this phenomenon of the Seebeck effect. And if you increase a little bit the temperature on the hot side, then more of the hot electrons will flow to the cold side. But on the same step, the electrical field will increase a little bit more. And from this statements, one can say that the voltage which is created is proportional to the temperature difference. And the proportionality constant is the so-called Seebeck coefficient, or frequently also termed as thermopower. The opposite happens if we consider a process where instead of hot and cold temperatures, at the very beginning, we inject electrical current into a loop. And this causes that due to the so-called Peltier effect, one end of the material becomes warm and the other end of the material becomes cold. So we can create a small refrigerator. and use the cold side to cool down, for example, electronics, the CPU, or we can cool down also a beer at home. The Peltier coefficient is, as you can see here, proportional to the Seebeck coefficient. That means a material with a high Seebeck coefficient is a material also with a good Peltier properties. And the third thermoelectric effect is the so-called Thomson effect, which tells us that if we have a temperature gradient along the sample, as it is indicated here, and if we switch on an electrical current, then additional current is generated, and this is known as the Thomson effect. And the coefficient of this Thomson effect is again proportional to the Seebeck effect. So the most dominating effect at all is the Seebeck effect. So these are the three scientists who have introduced this effect, as you can see, more than 200 years ago, here more than 180 years, more than 190 years ago, and the Thomson effect is slightly smaller. Unfortunately, not only the Seebeck effect is of importance in this thermoelectric energy conversion, rather we have to consider beside the Seebeck effect also the electrical conductivity of the very same piece of material, as well as the thermal conductivity. When putting these parameters together, we end up with the so-called figure of merit. So the figure of merit, when multiplying with absolute temperature, reveals a unitless constant, a unitless quality, and this is at its optimum if this constant becomes larger than 1. We have a second matrix, and this is called the quality factor. You can see here on the left side the figure of merit. It is a property which depends on quantities which we can measure, while on the right side there are more quantities which are direct materials properties, like the mobility of the charge carrier. So one can see the mobility of the materials is a very basic quantity which helps to discriminate whether a material is a good thermoelectric material or not. That means materials having a high mobility are considered as good thermoelectric materials, or they turn out to be good thermoelectric materials, and the opposite is true as well. In order to get large values of the figure of merit, we need to have large values of the Seebeck coefficient. And as I already mentioned, the Seebeck coefficient in a very first approximation depends on the charge carrier density. So if the charge carrier density is large, then the Seebeck effect will be small. And if the charge carrier density is small, then the Seebeck coefficient will be large. And the large Seebeck coefficient, as we have already seen, helps to generate a large voltage from a given temperature difference. Secondly, we need to have low resistivities, low electrical resistivities in order to avoid Joule's heating. And thirdly, we need to have in the material low thermal conductivities in order to maintain a large temperature gradient between the hot and the cold end of the sample. Now, here is again this quantity of the figure of merit. One can see the Seebeck coefficient is squared divided by the electrical resistivity. And this entire quantity is then divided again by the thermal conductivity. And as you all know, the thermal conductivity consists of an electronic contribution and of a phononic contribution. In order that we get ZT values larger than 1, you need to find materials which have a Seebeck coefficient about 100 microvolt per Kelvin or larger. Please notice that, for example, a piece of copper, a copper wire, has a Seebeck coefficient of roughly 1 microvolt per Kelvin. And the thermal conductivity on the other side should be as small as possible. So a good value would be roughly around 1 watt per meter and Kelvin. What you already can see from this matrix here is that, from my colors, that the Seebeck coefficient and the electrical resistivity is correlated with each another. That means, as I already mentioned, if the charge carrier density is large, then the Seebeck coefficient is small. But on the opposite, if we have a large charge carrier density, then the electrical resistivity is small. So it's just the opposite behavior. And there's a third correlation, as we all know, the electrical resistivity and the electronic part of the thermal conductivity are correlated again by the so-called Wiedemann-Franz law. That means a good electrical conductor, that means a material with a small electrical resistivity, is also a good thermal conductor. As a consequence, an optimization of materials is quite difficult, because if we improve one of these quantities, the other quantities just are doing the opposite way. Therefore, a lot of strategies have been developed in order to overcome this problem. Thermoelectric efficiency, ladies and gentlemen, is another feature. While the former one is a material-dependent property, the performance of a thermoelectric generator depends in addition on, as you can see here, on the Carnot prefactor. So a thermoelectric generator is a thermodynamic machine. That means it is of importance to have a large difference between the hot side and the cold side. If this difference becomes small, then the efficiency of a thermoelectric generator becomes small as well. So the best would be to have on the hot side several hundred centigrades, and on the cold side, just a couple of Kelvin. Third, as you can see here from this formula, the figure of merit, that means the material quality, just enters as the square root of ZT. That means if we are working hard for 10 years and improving for a certain material, the figure of merit from 1 to 2, finally we improve the thermoelectric performance just by a factor of 1.4. So this is summarized here in this diagram, where the efficiency is indicated here on the z-axis. Here's the temperature, and here's the figure of merit. So if we consider everything with respect to room temperature, for example, and if we would have a couple of 100 centigrade temperature difference, and if we do have a very good material, say with a figure of merit of 3, then you can see such a thermoelectric conversion would have an efficiency of about 0.3. So we are far away from an efficiency of 1. And unfortunately, nowadays material have in the best cases an efficiency of about 0.1. So everything what I said is summarized here in this diagram, as you can see. So here on the x-axis, there is indicated the charge carrier density. And on the y-axis, we do have different quantities, like the Seebeck coefficient, which decreases like 1 over n, where n is the charge carrier density. We can see that for very small numbers of the charge carrier density, 10 to the power 17 or 10 to the power 18, we have a large Seebeck coefficient. But on the other hand, as you can see here, the electrical conductivity indicated here as sigma is quite small. Please note that copper has a charge carrier density of roughly 10 to the power 23, so far on the right here. So one can see the Seebeck coefficient decreases as the charge carrier density increases, but the electrical conductivity increases. So you can immediately see that this so-called power factor, which comprises just the Seebeck coefficient and the electrical resistivity or the electrical conductivity, it builds up somewhere a maximum for a charge carrier density of roughly 10 to the power 20. So from this diagram, you can already see for which type of materials we need to look for 3 orders of magnitude at least smaller than the charge carrier density of copper. If we add the thermal conductivity consisting of an almost independent contribution from the lattice, it is only very slightly influenced from the charge carrier density, and from the electronic contribution to the thermal conductivity, one can find again a maximum in combination with the Seebeck effect and the electrical conductivity. But this time you see that the maximum is slightly different from the maximum of the power factor. And the difference is, if you are interested to get a maximum output from your source, then you should focus more on the power factor. So if you have a source which always produces heat and you do not need to have too much electricity, then the power factor is okay. But if you try to convert the largest percentage of heat into electricity, then we need to look for this so-called figure of merit. And as I already have said, we need to look for materials which are near to a metal to insulator transition. Okay, after this short introduction into the basic phenomenon, let me show you a few slides with respect to motivation and application. So this here is a diagram of the energy consumption throughout the world. There are huge numbers. It's not of certain importance how many multi-millions of tons of carbon we need to support our daily life and the industry. But you can see there is a steady growth. The very dark bars represent Europe, and this slight part here represents Asia. So one sees the energy consumption throughout the world keeps almost constant or even goes a little bit back in Europe, but in other parts of the world there is still a growth in energy. And this diagram constitutes the sources of energy. And you can see that coal, which is responsible primarily for CO2, still has a very, very large share. And industrial processes or our daily life generates from a primary source of energy a lot of waste heat. And if we would be able just to recover a certain fraction of all this waste heat, maybe it's more than 50 or 60% of all the heat which is on the primary side introduced, then we would gain a lot of electricity and thus would avoid a lot of CO2. Here is an example which is valid for combustion engine in a car. And if we put on the primary side 100% of energy, say from diesel or gas or others, then we get on the secondary side, that means which produces that a car drives with a certain speed, just 25% back. So all the other losses, for example, in the exhaust pipe, where the gas comes out with 500 centigrade or even above, makes about 40%. Then there are other processes which takes away the rest of percentages to 100. That finally, as I said, only 25% ends up in the effective movement of a car. So in the 2010 years, we had the idea to recover some of this energy which is lost as a waste heat from such a combustion engine. And we planned to regain about 2 to 5% of the primary input at all. And this would be a thermoelectric generator which is mounted in very near to the converter on the hot end of about 500 centigrade, as I already mentioned. And this could produce several hundred watts. We focused on a thermoelectric generator between 500 and 1000 watt. And there have been calculations saying that if we can generate 100 watt thermoelectric generators, then this would save about 1% of the fuel. There are a lot of other interesting applications, mostly niche applications, where thermoelectricity is already in use. And there are very famous examples, like this robot on the Mars, which is driven by a thermoelectric generator. It is a so-called radioisotope generator. That means you have a small piece, say, of plutonium in the center of a thermoelectric generator. And the decay of plutonium makes that this piece of plutonium becomes quite warm, 5, 6, 7, 800 centigrade. So finally, it is very hot. And on the other end, you have the cold surrounding of the Mars, which is well below our room temperature. That means you have a very big difference in temperatures, and thus you have almost ideal conditions to produce electricity by employing thermoelectricity. And this process, which such radioisotope thermoelectric generators, is extremely reliable. Possibly you heard just 1 or 2 weeks ago that the deep probe spacecraft of NASA in America, the Voyager, which was started 1977, was somehow restarted with its computer. So NASA was able to update or upgrade the computer on board of this deep space probe Voyager. And as I already said, all the electricity which is present at this deep space probe comes from thermoelectricity. So it shows us that a well-settled thermoelectric generator can serve us very many decades. There are several things which favors such applications. For example, this reliable usage, or the fact that you do not have any moving parts as you have in a generator, for example. Everything is noiseless, and also you do not have vibrations. And finally, you can generate electricity also in the night, for example, totally independent from any power grids. And you need not to go to make a service like you need to do with your car, because such a thermoelectric generator can run really long time. In a diploma work in my working group in Vienna, we have installed a thermoelectric generator in such type of wood stove, which might, for example, control and open and close with the electricity generated from this stove in order to open and close the windows here, or to drive a small fan in order to increase or to decrease the fire in this stove. So if you are sitting in some house in the mountains in 2000 meters height, you possibly will have such a type of a stove. And if you do not have electricity there in this house in the mountains, you can generate by using a thermoelectric generator in order to power your house as well. Possibly one driving force for future will be the Internet of Things, that many applications on devices or even with respect to a person can be powered by thermoelectricity. Clearly, in these cases, we will not have a power output of 1000 watts, as we need to have in a car, but already several microwatts are enough to power small parts of electronics, as it is indicated here. So from this picture, one can see that there are possibly two directions in the research of thermoelectricity. The one might be to have larger thermoelectric generators of the order of several hundred watts, and the other direction might be an application where just microwatts are of importance. Okay, now we know what we can do with thermoelectricity, with thermoelectric generators, and how the basic principles are working. But you know, as solid-state physicists, we like to understand why a certain material is good and another material is bad. And if we have a good material, we like to know how we can make it even better. That means we have to take into account a number of basic physics, possibly most of the things which I'm going to show you, you have already heard in your lectures here or elsewhere. Transport, ladies and gentlemen, in solids made by electrons or by phonons are dynamic processes. So it's much difficult to describe, much more difficult to describe the electrical resistivity or the thermal conductivity than to describe, for example, specific heat or magnetic susceptibility, because of the dynamics we do have in the systems when charge carriers or phonons move around. And I'm convinced you have already heard something about the Boltzmann transport equation as the most basic fundament of our understanding of transport processes, not only in solids, but specifically in solids. And if you work hard 1 hour on the starting point of the Boltzmann equation, you will end up with two fundamental equations. This is the so-called charge current density. That means how much charge is flowing through a certain cross-section per unit time. And equivalently, how much heat is flowing through a certain cross-section in a unit time. Possibly we do not need to explain all the parameters here, but what is of importance, as you can see here, is the velocity. So the velocity of the charge carriers determines how good or how bad the certain conductivity of a material is. Then here we have the unit charge. We have an electrical field which causes the flow of charge carriers. And since our electrons do have a half-numbered spin, as we already heard this morning, we do have to take into consideration an appropriate distribution function. And this distribution function is the Fermi-Dirac distribution function. And we have to consider this distribution function or the derivative of this distribution function with respect to energy. At 0 Kelvin, I think you remember yourself, it's just a step function. But as you can see here from this very first line, this charge current is not only driven by the electric field, as we do have in general the impression, but also, as you can see here on the right end, electrical current is driven also by a temperature difference. And again, very similar quantities appear here in the second part of the equation. A very important parameter here is the so-called relaxation time or the living time of a certain particle. And this relaxation time measures the time between collisions of the particles with other scattering centers, for example, impurities. And here you can already see if the relaxation time is small, that means one particle, one electron, can travel only a short distance between collisions, then the charge current density will be small as well. And in a material which is not perfect to 100%, you always have such scattering events, even at 0 temperature. But as soon as the temperature is away from 0, your lattice will start to vibrate. And this means you have additional scattering of electrons and phonons. And all these specific scattering processes are summarized within this relaxation time. Of similar importance is the heat current density, where also the velocity plays a role, but differently to a simple assumption in the charge carrier density, the energy, of course, plays a significant role as well. Since we do have metals, the energy is just of importance if there is some distance to the Fermi energy. Because we remember a particle can be scattered only or can move only if there are free states. And free states in a metal are just in the proximity of the Fermi energy. And again, the linearized Boltzmann equation shows that the heat current density consists of a number of terms as well. And while we usually assume that heat is driven just by a temperature gradient from the hot to the cold side, you can see from this equation here, from the red colored equation, that heat is driven also by the electrical field. So this is my most important take-home message today. If you understand this or accept this, you understand very many thermoelectric phenomena. Charge is driven by a field, but also by a temperature gradient. And heat is driven by a temperature gradient, but also by the electrical field. Then making a little bit cosmetic, as you can see here, some of the parameters are summarized in so-called transport quantities. One can see that the charge current and the heat current density can be expressed in a quite simple form. And if you use these simple forms here, you can even think about how to measure these quantities, how to simply measure these quantities. You know, in case of an electrical resistivity, we do not have a temperature gradient along the sample. So this second term goes away. And the electrical resistivity is then proportional to the electrical field. And the proportionality constant is nothing else than the conductivity. So the electrical conductivity is given by this K0 transport integral. And then you can see 0 means here 0. There is no energy of importance. The only energy dependent term is this derivative of the Fermi-Dirac distribution function. And if we like to measure thermal conductivity, then we will not have a flow of electrons, a steady flow, a dynamic flow of electrons. That means this Q can be set to 0, and then you can evaluate from these terms here already a method how to measure the thermal conductivity. So as you can see here, this term here on the far right part of this transport integral is called selection function. It's this energy difference and the energy derivative of the Fermi-Dirac distribution function. This seems to be material independent, so it's only temperature dependent. And the left term here clearly is a material dependent quantity because the velocity of the charge carriers is dependent on which material or which Fermi temperature the material has, and clearly the relaxation time depends on pretty much the same processes. So we have seen that we have transport integrals K1, we have transport integrals K2, K0 as well. That means 1, 0, and 2 makes or is important for this exponent here, for this exponent n, and the so-called selection function. So the most simplest one is the electrical conductivity, because as we have already seen, the n is 0, and therefore the selection function consists just of the energy derivative of the Fermi-Dirac distribution function. What does it mean? It means if 0 points out the Fermi energy of the material, and if we increase the Fermi energy a little bit, or say better the chemical potential, or if we decrease a little bit, then different parts of this electronic structure in the vicinity of the Fermi energy are going to contribute to this charge carrier density. And clearly there's a difference for this derivative, whether we have, for example, 300 Kelvin or 1000 Kelvin. The Onsager coefficient, please note, this is nothing else than the Seebeck coefficient multiplied by the electrical conductivity. So the electrical conductivity is simple here, but then you can see that the Onsager coefficient and thus the Seebeck coefficient varies a little bit different in comparison to the electrical resistivity. Because the first derivative, or the entire quantity here, shows that it is an uneven function. That means if we have a situation where the Fermi energy is slightly shifted above zero, then we do have positive contributions, meaning that the Seebeck coefficient will become positive. Or if we have energy slightly below, then here you can see everything is negative. And it is again this width of the distribution where electrons or holes are contributing to the transport. Again, everything is much broader if we have increased our temperatures, say to about 1000 centigrade. The electronic thermal conductivity, remember, this is somehow dependent on the electrical conductivity, is slightly different with respect to the electric conductivity, because we do have this prefactor. And it turns out that due to this prefactor, this selection function is an even function. That means independent whether we are slightly above or slightly below the Fermi energy, we always do have a positive contribution to the electronic thermal conductivity. That means we do not have negative, we cannot have negative values of the thermal conductivity. And the same holds true if we consider the phononic-driven thermal conductivity. Clearly, we can no longer use the Fermi-Dirac distribution function. Rather, we have to employ the Bose-Einstein distribution function. Here is a small examples of two entirely different type of materials. Always on the left side, there is the density of states plotted as a function of the energy for silicon. And on the right side, there is the density of state plotted for aluminium in the vicinity of the Fermi energy. We know aluminium is a piece of metal, so the density of state very near to the Fermi energy is almost structureless. And on the left side, the electronic density of state of silicon, note this is a much larger representation than in fact it is with in comparison to aluminium. Silicon clearly is an semiconductor, and thus we do have a gap in the electronic density of states of almost 0.7 electron volt. And now if we apply this selection function for the electrical conductivity, for the Seebeck effect, and for the electronic contribution to the electrical resistivity, this selection function are blue framed here and represented here in orange for the 1000 Kelvin case and in green for the 300 Kelvin case. So this selection function selects somehow this range where the electronic density of states or where the charge carrier can be used, for example, for the electronic transport. And then in order to define the entire quantities from this linearized Boltzmann equation, one has a prefactor, this material dependent factor, as I already said. Please note that this material dependent factor is simple only in the case if we assume parabolic bands. And as you can see here, these parabolic bands depend on the density of state, on the velocity, and on the relaxation time. And these graphs help to understand why silicon has a large value of the thermal power and a small electrical resistivity. And the aluminium has a large value of the electrical resistivity, a large value of the electrical conductivity, but a small value of the Seebeck coefficient. Let me go back. You can see when expressing the Seebeck coefficient with respect to all parameters, then there is this part and there is a second part in the numerator and in the denominator. And in the denominator, this part equals the electrical conductivity. So we can already see here when the electrical conductivity is large, altogether the Seebeck coefficient will be small. And this can be expressed by simple assumptions as it is indicated here. So from our experience, we know silicon has a large value of the Seebeck effect and a small conductivity, and aluminium has the opposite features. Now, what can we do with these basic concepts of the Boltzmann transport function? We can try to model the transport quantities which we observe from experiment, or we can try to calculate all these transport quantities as a function of temperatures from first principles. And let me start with so-called DFT calculations. Possibly you know that in Vienna, two very famous programs for DFT calculations. Okay. Maybe I will finish this DFT and then we make a stop. Two of such program packages, the Wien2K and the WASP, have been developed. And in the context with the program packages like Boltztrap or fermion, one can calculate pretty much properties of simple materials. Clearly, materials which do not have too much electronic correlations. So what we have calculated, for example, in the case of iron 2 vanadium aluminium, this is a so-called full Heusler compound. And you can see here is the dispersion into several high symmetry direction and here is plotted the energy, and at 0 we do have the Fermi energy. You can see from this results that at the gamma point of this material, the valence band touches almost the Fermi energy, and on the X band, the conduction band is slightly below the Fermi energy. So if this calculation is true, then this would be a typical example of a semi-metal. This can be seen also in these graphs, where then the electronic density of state is represented as a function of temperature. We have switched on also some Coulomb correlation strengths, and the result of this Coulomb correlation strengths is that both bands move a little bit against each other, making from a simple semi-metal a simple semiconductor. And here is again this energy distribution of the Fermi-Dirac distribution function. You can see at 200 Kelvin or at 700 Kelvin, different portions of this dispersion relation contributes to the observed quantities, like it is the case in the Seebeck coefficient. Once again, one can see here the Seebeck coefficient depends on this transport integral K1, and on K0, we remember ourselves, this is proportional to the electrical conductivity. Iron to vanadium, aluminium is a cubic system, so the direction dependence is not pretty much of importance. And just using these quantities, which have been seen on the previous slide here, and making the first derivative of this energy dispersion of the electrons, we gain the velocity. So the most important quantity in the Boltzmann transport equation, as you can see here, and thus we can calculate these transport integrals. Unfortunately, right now there are no methods how we can calculate this relaxation time. So usually we assume a constant relaxation time and then try to make an appropriate calculation. And you can see when having this Coulomb correlation strength, at least the position of the maximum or the movement of the Seebeck coefficient through 0 can be represented. And as we have seen on the previous page, so electrons from this band are contributing, and holes from this band are contributing as well to the total Seebeck effect. So we have contributions from above and from below, and the summation of both effects reveals the entire Seebeck effect of the material. Similarly, we can consider the electrical resistivity. Here is plotted the electrical resistivity as a function of temperature in a really broad range of temperatures from 4 Kelvin to 900 Kelvin or something like this. And by using, again, a constant relaxation time, one is able, at least at higher temperatures, to account for the temperature-dependent electrical resistivity. Also, we are using supercomputers. We are not really able to represent, say, to 100% the temperature dependence of important transport quantities which determine the thermoelectric power of a certain material. Okay, Finally, from this DFT section, we can calculate the phonon dispersion. So plotted here is the phonon dispersion as a function of energy, here represented as terahertz. 1 terahertz is about 50 Kelvin. And you can see we do have acoustic phonons. And again, the velocity of these phonons is proportionality to the slope of these phonon branches. And the other phonons here are the so-called optical phonons. And again, when using these phonons, as have been shown on the previous page, we can account for the temperature-dependent thermal conductivity. So the thermal conductivity, the measured thermal conductivity is plotted here. And these solid and dashed lines are calculations under certain assumptions. What one can see is that at least at high temperatures, the phonon thermal conductivity can be nicely calculated from DFT-based modeling. At low temperatures, however, one can see that we are far away from the reality of our measurements. Okay, at this point, we can make a short stop.